Hi friends, Ben again. This is a video for the Calc 3 class. We're looking at Taylor series, which, as I will constantly joke, are completely different than power series in every way. They're not. It's the same thing, just with a different emphasis. The main things that we're going to emphasize with regard to Taylor series that we didn't touch on with power series are, number one, how you get a series for a particular function. We did that a little bit with functions that you could derive from the geometric series, but now we're going to look at what to do with it in more general. Then the second thing that we'll do is take a look at what's referred to as Taylor's theorem. And if you're reading your textbook, they will make a distinction between the Maclaurin series and the Taylor series. All the Maclaurin series is a Taylor series that's centered at 0. Why the two names? I think that Maclaurin probably originated these, and then Taylor gets his name attached because of Taylor's theorem. Taylor's theorem is something that allows us to get estimates for the power series with just a truncated number of terms. Okay, so let's take a look at the basic stuff here. And all right, so maybe it'd be better if I turned that sideways. All right. So your basic notion with these Taylor series is that you're going to have, well, your f of x being some summation with these a sub n's times the x minus c to the n. If it's a Maclaurin series, then it's just x to the n, okay? So the thing that we need to notice here when we expand it out like this is if you plug in the value c to any of these terms past the first one, poof, they just disappear. So that means that your f of c needs to actually be a0. But then we could take the derivative, f prime of x, and just go through and differentiate term by term. Naturally, the a0 disappears, but then you've got a1 as your constant term, 2a2, 3a3, 4a4, and so forth as your coefficients of the various powers that go on down there. And if you take that and plug the c in, well, once again, all the higher powered terms just vanish. And that means that your f prime of c is going to be a1. Now, I'm bizarrely going to write that as f prime of c divided by 1. And you'll see why here in a second, because we do the next derivative, and watch what happens. We just get the terms marching their way to the front, and they just drop off powers of x as they go because of the derivatives. But now this time, since our f double prime of x has a 2a2 as that leading term, when we plug in the c, we're going to get 2a2 is equal to our f double prime of c. So that means our a2 is going to be f double prime, the second derivative, evaluated at c, divided by 1 times 2. And when we do the third derivative, we'll get a 1 times 2 times 3, and so forth. So that our formulation we actually get is that the nth coefficient there, the a sub n, is going to be just the nth derivative evaluated at the center and then divided by n factorial. Okay, and that's what I've got on that bit there. But now we want to take a look at some examples for this. And this first one here, let's take a look at e to the x. Well, e to the 2x. We all know about the derivatives of e to the x. Super nice function. You take its derivative and you just keep getting the same thing back over and over again. In fact, that is one way to define e to the x, is to just say it's the function that when you get the same thing back from its derivative. So we're looking for e to the 2x though. And what I want you to notice, and you probably have had this come up in a calculus class before, as you take the derivative of e to the 2x, you just pick up a power of 2 each time you go down there. So if we're evaluating it at 0, because remember we said Maclaurin series, so if we're evaluating it at 0 there, then the thing that we'll have happening is that all we get for these terms here is going to be the climbing powers of 2. So once you've noticed a pattern like that, you can go ahead and say what your a sub n is, that it's 2 to the n divided by n factorial, and then you can write your series by just saying it's a summation n equals 0 to infinity 2 to the n over n factorial x to the n. Boom, done. Okay. Now, that hopefully is a little bit heartening, because on the previous ones you were having to constantly say, oh, what's the interval of convergence on that? Well, a lot of these that we're going to talk about here, not all of them, but a lot of these are going to have intervals of convergence that actually go out to infinity. So if you notice on that last one there, it had factorials in it. And so when you do the ratio test in it, you're going to end up with an x divided by n plus 1, then absolute value, and the limit is n goes to infinity. That'll get you 0, which is always less than 1. And so anytime you have that happening as you're trying to find the interval of convergence, then you get infinity for your radius of convergence, or in other words, minus infinity to infinity is the interval, the whole real line. So let's take a look here at another one. And I've tried to pick one that is a little bit like one of your homework problems, but not exactly the same, okay? And so this time we're trying to find a Taylor series for sine x. So if you look at the end of your section, they just give you the Maclaurin series for it. And you ought to go through, I think there's an example where they work that out. You ought to go through and see how that gets worked out. But we're going to do the one for sine x at pi over 2 just to have something that's not centered at 0, okay? So first thing is to notice what happens with sines and cosines as you take the derivatives. Once you get to the fourth derivative, you're repeating, right? And it's just going to cycle around and do that over and over again. So for what we want to do, we want to plug pi over 2 into all those derivatives. With that idea in mind, it's going to cycle around. Of course, the sine of pi over 2 is 1, but the cosine of it is 0, okay? And then if you notice, that just means that all of these even derivatives here are going to zero out on you, okay? And then for the odd derivatives, those are going to go 1, minus 1, 1, minus 1. So they're going to alternate after that. So our even terms, the way we can express that you're doing something even is to refer to 2n. And then things that are odd, we can refer to them as 2n plus 1 or 2n minus 1. You could put any odd integer in there in order to add or subtract in order to make odd ones come up. And you just pick plus 1 because of the fact that we want to be able to get the first term there where it was the, haha, I think I just spotted an error on my part. Anyway, we want to pick out here and get these even terms as opposed to the odd terms. Sorry, I said it backwards a second ago. The things that are zeroing out are the odd terms, right? So since those are zeroing out, we just don't bother writing them. So what we're going to write is a sub 2n. And the reason that we want to break it like that and say a sub 2n is because we can see that pattern that we are getting a 1 and a -1 back and forth. We need something like the -1 to the n. Now, when you do one of these and you're trying to write the pattern, write -1 to the n, and then go back and see, does that fit? If it's one off, then instead of using -1 to the n, you might want to use -1 to the n plus 1 or n minus 1. But in this case, I'm just so clever that I managed to get the right thing the first time. So, all right. Then continuing on here, once we know that we want to have that -1 to the n power, in order to have it be +1 this time and -1 this time and +1 this time, okay? Then that's why we have that n power there. Okay, and then we're dividing by the 2n factorial because that has a 2n in that subscript, and we know that we're supposed to divide by that same factorial down there. Okay. So once you've got that going, then you can just write this a sub 2n down here as your coefficient. And because our center was pi, we say x minus pi to the power. And the power we have is the 2 n's because those were the powers, those were the coefficients that we actually had that were not zeros. Okay. So if you look up the power series / Taylor series / Maclaurin series, whatever you want to call it, for sine of x, it won't be that one. They will give you the Maclaurin series because that's the one everybody uses. Since the interval of convergence goes -infinity to infinity, it doesn't matter. We can always use the Maclaurin series. But I was making an example just to show you how you would do it if you had something different. So, all right, let me find the right thing on here. Taylor series example 3. All right. Oh, and I can share it with you. Haha. So, like before, screen mirroring. All right, so this example 3, and you'll notice that this one is very much like one of your homework problems. So we're trying to find a Taylor series centered at x equals 1 for the function x to the 3/2. I thought about trying to do something with some different power. Sorry about that. And I thought about trying to do some different power, but really multiples of 1/2 are going to be the ones that will make most sense to do in this. Okay. So what we're trying to do is to see how the pattern matching goes of trying to set up these derivatives and figure out the coefficients. This one's not easy, okay? And by making it 3/2 instead of 1/2, like you'll have in your homework, probably made it harder. But here's what I want you to do, and ignore me at your peril. I'm trying to guide you on what's the easiest way to get these figured out, okay? So you write down your function, and then you start taking derivatives, okay? But when you start taking derivatives, the first one's not hard. The second one, you have to do a little bit more. Your instincts, what you have been trained to do by generations of high school math teachers, simplify everything. Do you know why we ask you to simplify everything? So that we can grade 5,000 problems a day and everything has to be in exactly the same form. I'm not grading that many problems per day, so, you know, I'm I'm more concerned with your being able to see what's happening here. So as you take these derivatives, just line them out. Don't simplify until you have to. So notice what's happening. We'll have 3 halves, 1 half, minus 1 half, minus 3 halves. The next thing we'll pick up is a minus 5 halves, then a minus 7 halves, and a minus 9 halves. You could do as many terms as that as you really felt like doing, right? But we want to write a formula for it so we don't have to. Once we have a formula for it, we can let the computer do approximations for us. So we have to notice what's happening with each and every one of those. And so I think you can probably see it early on, but really it starts to show itself here with the third derivative and then the fourth derivative. And if we wrote the fifth derivative, we'd see our first couple of terms do one thing, and then after you get to this third derivative, so n is greater than 2, after you get to this third derivative, then you start alternating. And it's going to alternate every time after that, but it doesn't alternate until it starts there. Frustrating? Yeah, because sometimes it's not easy. Most of the time it's not easy. But then the other thing that you should be able to see immediately is that there's going to be powers of 2 in there. So this one, let's see if I can just take that out. So this one we've got here, we will end up having a 2 to the third, and I didn't leave enough space for that. 2 to the third. Whereas the previous one, we had a 2 to the second, and the next one would have a 2 to the fourth. Well, our n is 3 in here, and n 4 in here. So that part's nice. We can see we're going to have a 2 to the nth power, okay? Then the alternating part of it, minus 1 to the n. Check and see. At n equals 3, it's odd, and you've got a minus. At n equals 4, it's even, and you get a plus. Boy, I hate that. Okay. Then that piece of things we can have figured out, but we have to be dealing with it where the n is greater than 2 for those patterns to actually come up. And then the top of what you're working with is the hard part. It goes 3, 1, minus 1, minus 3, minus 5, minus 7, et cetera, et cetera. We've already taken care of the minuses. So what we're going to have to observe is just that it's going 1, 3, 5, 7, etc. After the n equals 2, you get that pattern starting to emerge. Remember how we had a problem in the ratio series stuff where it went 1, 3, 5, and ... up to 2n plus 1? So this is exactly that coming up, right? So how do we handle this? Carefully, right? Let me adjust this down a little bit here. So a sub 0, so n equals 0, we plug in and we figure out where it is. We know that our pattern doesn't really start until n equals 3. So for a sub 0, a sub 1, and a sub 2, we're just going to plug in the numbers and calculate them. But we'll notice that there's a 3 hanging in at the front on all of those. And then after n is past 2, it starts up this pattern here. 1, 3, 5, blah, blah, blah. You know it ends at some odd number. So let's just pretend that we're trying to figure this out at the moment, okay? You had figured out it's 2n minus something, and you just don't know what yet. So you think back and say, well, I want to match what I have in my pattern here. So let me try 2n minus 1, okay? And so for n equals 3, the place that it ends is here at the 1. So 3 times 2 times 3 is 6, and then minus 1 would be 5. It doesn't end at the 5, it ends at the 1. So that sounds like 2n minus 1 is not subtracting enough. So then we go back and say, all right, what if I did 2n minus 3 instead? And then we check back and see that when I plug in n equals 3, I want it to end at a 1, then that's not going back far enough, right? Or we could look at n equals 4, that we're not going back far enough here if we want to get it to end at the 3. So for n equals 4, you'd have 2 times, damn it, 2 times 4 minus, we wanted it to end at what on that? We wanted it to end at 3. So 2 times 4 minus something equals 3. So 8 minus, looks like 5 ought to work, right? So we put in here, come on, 2n minus 5, right? So that, then the other part that we'd already figured out, the 2 to the n minus 1 power, n plus 1 power, and then the n factorial comes in because that's just part of our Taylor series definition, okay? So that says that we've got formulas for our a sub n's, and we can just say, screw it, we can just say, heck with it, and right here say, summation n equals 0 to infinity a sub n times x minus 1 to the n, and just have our a sub n specified elsewhere. Perfectly fine to do. In practice, they tend to not do that, though. They tend to do this of, we'll just go ahead and write out the first few terms. And so I went ahead and jotted out those first 3 that didn't quite fit the pattern here. And then with the next couple of terms, I tried to develop the pattern where it would be seeable. And then I put a plus dot 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 plus, and then I wrote out the formula for the nth term. And then a plus dot 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 at the end. Remember that plus dot 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 at the end, that actually says it's an infinite series. If you're truncating it, then you would have some place that it stopped at. And so, for instance, the S sub n, the partial sums that we get, would be there with an ending and not a plus dot 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 on them. So, all right. Let's take a look at one more example here. And this is the thing where we use Taylor's theorem, okay? So for Taylor's theorem, I'm going to have us do one here. It's not super rough, but you know. So with this, we're going to be asking to approximate e to the minus x dx, the integral from the integral from 0 to 1. Damn it, 0 to 2. I originally thought I would do 0 to 1, but that made this example too easy. And so I tried to jazz it up a little bit. Not a lot, just a little bit. All right, so we're going to approximate this with an error no more than 0.01. If you are a practical sort, you are throwing up your hands and saying, why did Ben not just plug this in the calculator? I mean, hell, even when we didn't have a calculator to do this, I would go use Mathematica or Python or something and just get an approximation there. That's what we always do. There is a madness to my method? No, a method to my madness. A method to my madness here. This sort of approximation stuff that we do, there are problems in rocket science, any sort of a hard science that has a lot of measurements in it, where you have to do modeling and you have stuff where you don't actually have a formula. You can't just say integrate this because you don't have a formula to integrate. And what you're doing is writing a program in order to approximate answers to the model. And so you have to use stuff like this, and you have to have some idea about error bounds. So this is more than anything just exposing you to error bounding techniques that might come up when you're trying to send somebody to Mars, or if you're trying to get your Alcubierre drive online. I probably pronounced that wrong, so I'm sure he'll forgive me because he'll never know who I am. But all right, no, I don't need to cut or copy this. Thanks. All right, first thing is this series for e to the minus x. We did that in the previous example, okay? So if you're wanting to actually get the integral of that, what you'll actually do is to just integrate your power series term by term. But you don't want to have to do infinitely many terms on this. So we're going to tackle this with Taylor's theorem. So Taylor's theorem, you have a statement of it in your problem set, but it says that if you break the infinite series down into two pieces, the nth Taylor polynomial, so write S equals the nth Taylor polynomial plus the remainder pieces. So this here is the first n terms. And this here is the other infinity terms. Because anytime you truncate something and just do the first 5 or 17 or 83,000 terms, no matter what happens, it always has an infinite number of terms that you're leaving off. Just the nature of infinity. So this R sub n that we've got there is referred to as the remainder. And Taylor's theorem says that when you get the remainder for the nth Taylor polynomial, that the actual value of it will come out to be the next derivative evaluated at, and notice I just put a squiggle there. It's not at x, it's not at c, it's some number between x and c. And traditionally we use that variable, I think it's called psi, but I always just write a squiggle, okay? Anyway though, f's next derivative evaluated at some number between, and we have no idea which number between, divided by this n plus 1 factorial, and then times your x minus c to the n plus 1, okay? I will not try to prove that for you, and I will not burden you with having to know the proof, okay? So when we're working with this, because we never have a value for the psi there, we just know it's something between x and c. what we end up doing is taking and estimating the function. Now, for our purposes, we've got e to the minus x. No matter how many derivatives you take of that, you're getting either plus or minus e to the minus x. So if we think about how big that gets in the interval from 0 to 2, it is actually a function that you can graph, and it is going downward. The biggest value is at the left end. Now, if you're doing sine and cosine, you don't worry about any of that stuff. You just say, yeah, sine and cosine is always between -1 and 1. But with this particular one, we are able to get a fairly sharp estimate of it based on the fact that it is a decreasing function. Okay, so instead of writing this f of blah, 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 we just replace it with the biggest value that it could be. So since it's always less than or equal to 1, then we're going to go ahead and just replace it with the 1. Then this x to the n plus first part in there, we also can put an estimate on that. Since the x is between 0 and 2, the biggest thing there is going to be to plug in x equal 2. And so our estimate here, the biggest it can be is 2 to the n plus 1, and then divide by n plus 1 factorial. Now, if you're doing a nice problem, you would be able to have a function there like 2 to the n, or n to the 15th power, or something like that, where you could just set it equal to your error bound and just figure out what the number is. I did not take that route. I chose one here where we can't just solve for it like that. So if you can't solve for it, and when you set it less than your error bound, okay, so we have our remainder error bound, and we just set it less than what we want as a maximum error. We just plug in values until we find something that it's lower than. Now, with regard to that, what I did on this is to, and let me just show you as I do it. I just came over here to Microsoft Excel, and I said, okay, 0, come on, 0, 1, 2, 3, 4, okay? And then I looked back at the formula there. It said, and I have to say equals 2 to the power, parentheses, the thing next to me, plus 1, okay? The reason that I want to have it point at that positionally and stuff is that I'm going to copy it down to other cells, and the formula will continue on. Divided by, I had to look up the formula for factorial, and it's called fact. They don't abbreviate average, but they do abbreviate factorial, because, you know, you type average way less. Okay, but then we're divided by the factorial of that thing plus 1. Close parentheses, and I hit enter. And I'm just going to copy that down positionally, and you can see that it goes 2, 2, and so on and so forth. So, because I want to just continue that pattern a long time, I'll just pull this down and tell it to continue down there 20 places. And I look for the first place that it's less than 0.001. Notice here it's 0.0014, okay? And did I put the, hang on here. Let me just check my formula there. Plus, yeah, okay. So with regards to that, you can see that at n equals 9, that you're getting this value of 0.00028 something, so 3. Whereas when you were doing n equals 8, it was just a little bit bigger. So I'm going to jot that down in my notes for y'all real quick here. So n equals 8, it was 0.0014. Okay. And so when you're dealing with this, you're going to use n equals 9 for this summation here. And since we're doing that, come on, then we just need to take and do the sum on these. And I'm going to jump across here to the other screen and show you real quick here. So, so we're going to use a spreadsheet to do this, but maybe I write down what it is we're going to do. We remember that we had to integrate up there. What was it? Oh, I'll have to look back and see. It was x to the n dx, all right? So we'll have to go from 0 to 2, x to the n dx. And that's going to give us 1 over n plus 1, x to the n plus 1, evaluated 0 to 2. And that's going to give you 2 to the n plus 1, divided by n plus 1, and then minus 0, right? So what we have to do is for our summation here, n equals 0 to 9 of, oh, I've already forgotten the first part of it, minus 1 to the n, minus 1 to the n over n factorial, and then times 1 over n plus 1, no, 2 to the n plus 1 there. So summation n equals 0 to infinity, minus 1 to the n, 2 to the n plus 1, divide by, hey, look at that. I could combine those two together and have n plus 1 quantity factorial. Coincidentally, that's almost exactly the formula that I had before, right? So I am going to jump back over to my spreadsheet again, and I am going to adjust my formula, okay? So the thing that I am missing in there is that I need to have a minus 1 to the n. Otherwise, it would be the same formula. So I'll put minus 1 to the n. Nope, not to the n, to the power to my left, and then times, okay? And then I'm going to have to copy it to these. And notice that the only difference that really made was that you had negatives cropping up every other time. So we needed the ones from 0 to 9. We don't care about the others. And then we will say equals sum parentheses, highlight the ones you want to add up, close parentheses, enter. Boom. And we're getting about 0.8646. I might just go ahead and say it's a 0.865 because of how we were asked to approximate. But you know, my instincts are always to go to that 4th digit. So, all right, that's using Taylor's theorem. And I think you got like an optional homework problem like that. So take a look at that. If you have a rough time with it, ask about it. But that's probably the hardest thing out of the Taylor series stuff. Okay. All right. See you in class.